Okay.
Is that not work? Oh my gosh.
It's okay. Thank you so much.
Technology,
good.
right?
I know.
Technology.
And then I got a new laptop, and they have the new old chargers.
Oh.
The new laptops have the old chargers,
Wow.
but the Thunderbolt still works fine.
Oh, okay.
Here,
That's mixture.
it's very
That's
odd.
terrible.
Yeah, consumerism.
Okay. So how this is gonna run is that this is gonna be a review session by Elysia. See ya. Good luck with your final. It's gonna be like a Q&A session, so I'll just answer like whatever you guys want to go over or any practice problems. Because I don't have anything prepared for this, so I'll just answer like you guys' questions. How are you guys feeling about the new material, or do you guys want to go over the old material? Uh-huh.
Yeah.
Old material, carboxylic acids.
I feel like
Uh-huh.
I don't understand amino acids that well.
Amino
Yeah,
acids.
anything about that.
Like amino acids. Okay. Okay. Yeah, amino acids. Let's do amino acids. Okay, so let's do it one by one. Okay. So amino acids is going to be a type of structure that will have an amino group and a carboxylic acid group, right? So it's part of the name. This is the amino group. This is the carboxylic acid group. If this is the carbonyl-carbon of the carboxylic acid, this is going to be the alpha carbon of the carboxylic acid, right? And this alpha carbon here will have some sort of R group, which is what we're going to call the side chain. And that side chain is going to be different for all 20 amino acids, right? And the side chain here, it could have different properties. Like it could be aliphatic, polar, non-polar, acidic, or basic, right?
Is it always going to be coming for this?
Yeah, the amino acid will always have this type of structure, but they could have different protonation forms, right?
Oh no, I'm saying like the R group. Is it always
Uh-huh.
going to be coming towards us?
Oh, for most cases, yes. If it's like this, but if it were to be going down like this, where you have the carboxylic acid right here, it's gonna go away from you, and that's a good question because most amino acids are S configuration, right? So if we were to assign priority for this chiral center here, right, this would be our number one atom because nitrogen has the highest atomic number, and let's say this is carbon, right? This would be number two, and this would be number three, right? The side chain. It's usually number three. Usually the side chain is lower priority group than the amino group and the carboxylic acid. If we go this way, counterclockwise, that is going to be S, and it stays as S because the hydrogen is already on the backside, the dash, right there, right? So that's why it's S, and the reason why if it's going to go down here, this is a dash, is because if this is 1, this is 2, this is 3, it looks R, right? But it is actually S because the lowest priority group here, hydrogen, is on the front side. So if it's a wedge, we just flip whatever it looks like when we assign priority. It looks R when we do that because it's going clockwise, but it's not actually R. It is actually S because the lowest priority group is a wedge. Like that. Yeah.
I'm sorry, this is
Uh-huh.
something I've been struggling with for a while. Can you please explain priority, like how you pick
Mhm.
each of those as for example?
Yeah. So priority is going to be based on atomic number, right? So the atomic number. So if we look at this chiral center here, and let's say I'm gonna use valine as the side chain, right? Isopropyl. If we're looking at this chiral center here, we're gonna compare this nitrogen, this carbon, and this hydrogen right here. Nitrogen has the highest atomic number if you look at the periodic table, so that's why nitrogen will have the highest priority group, right? Now, carbon and carbon here, they're tied because they're the same atom, right? And when they're tied, you look at what is attached to this carbon, ignoring the bond to the chiral center. This carbon here is bonded to oxygen 3 times, right? 2 from the double bond, 1 from the single bond here. So this carbon here is bonded to oxygen 3 times like that, OOO. Whereas this carbon here, it is attached to carbon 2 times and a hydrogen, invisible hydrogen, like that, right? And we see that this oxygen here has a higher atomic number than this carbon, which is why this is number 2. making this number 3, this carbon number 3, and then this hydrogen here is number 4, the lowest priority group, and that's how we assign priority for RNS. Yeah.
Could you go
Uh-huh.
over the synthesis of amino acids, like with the HPC?
Yes. Let's go over the synthesis, like HVZ, Strecker synthesis, and the other one, and and Edmond degradation. That's something else. That's like cutting the amino acids by the N terminus one by one.
Yeah, but then it forms the product, right?
The products. Oh, wait, let me see. Yeah.
Hold on.
Uh-huh.
Where is it?
Yeah, this one. Like that?
Edmond degradation, NCS, DCC, amino acid. Oh no, this.
You could do a peptide bond.
This is cutting the peptide chain by the N terminus
Yeah.
one by one. So this is the N terminus. This is the C terminus. Edmond degradation cuts the peptide one amino acid at a time at the N terminus.
I see.
Right. Right. So we'll go over that too. Edmond degradation. And DCC and the protecting groups like CBZ, Bach protecting group, like that stuff. Like I'm a little bit iffy with, so I gotta check my notes with that as I teach you guys. So that's more biochem stuff. Right. Yes, question.
Just like generally,
Uh-huh.
like after their questions, could you
Yeah.
go over like the other reactions in 26 as well?
26. Yeah, other reactions is chapter 26. Yeah.
Including those.
Right. Yeah. So let's do. You guys are familiar with the PI, PAH, pKa, and stuff like that, like how to find the protonated state and PI. Okay, it's good. So, synthesis of amino acids. There's gonna be 3 routes. The first route we're gonna talk about is the Volhard Zielinski reaction, HVZ reaction. Right, which is the HVZ reaction, right? So this is gonna review chapter 19, where let's say that we have this carboxylic acid here, and let's say we react it with Br2, PBr3 trace. What would this reagent do to this carboxylic acid here? Yep, it would add a bromine at the alpha position, so it's gonna do alpha bromination, right? Add a bromine at the alpha position. If this is the carbonyl position, this is the alpha carbon. One carbon, the first carbon, away from the carbonyl carbon. Right. So we're gonna add bromine at this alpha carbon, alpha bromination. Right. So this carboxylic acid here is gonna be our carboxylic acid of the amino acid. This is the alpha carbon of it, and this is gonna be eventually be our amino group. But to do that, right, we're gonna put ammonia. Right, ammonia, and there's some other reagents like I think like 25 degrees Celsius, 4 days. But the most important thing here is the ammonia, NH3, right? Because NH3 is going to do SN2 reaction. This is going to attack that carbon, kick out the bromine, to give us this carboxylic acid here. Right, where the ammonia will substitute the bromine by SN2. This N here is going to attack that carbon, kick out the bromine for SN2. Right. Now we have our amino acid here because this is our amino group. This is our carboxylic acid group. This is the alpha carbon right there. Right. Yeah.
Does that mean that like our product is limited to what side chain is already there? Like
Yes, our product is limited to what side chain is already there because we don't get to choose our R group, right? This is our R group here, which is already preset by the original carboxylic acid molecule. We don't get to choose that. But there is one route that we can choose the R chain, which is the Gabriel synthesis route, right? Right. But in the final products here, we're gonna have this NH2 protonated as NH3 plus, and this carboxylic acid deprotonated as carboxylate right there, right? Because think of this NH3 as a base as well, which is gonna deprotonate that carboxylic acid to the carboxylate. And this amino acid here, where the carboxylic acid is deprotonated and the amino group is protonated, is at physiological pH. Physiological pH, like around 7.2 to 7.4, right? And this is what the amino acid structure would look like at that point, right? The protonated state. And when you have a net charge of 0, where the positive charge and negative charges cancel out, we call that the Zwitter ion, like that, right? Okay. So now that is the first way, Helmholtz-Zielinski. Another way is going to be Gabriel synthesis, right here, where you get to choose the R group now. So I forgot what chapter this was. This was probably chapter like, I mean, chapter 23 or 20, 21, right? Where you're going to have this phthalic acid to begin with, let's say. Phthalic acid, which is a benzene ring with 2 carboxylic acids next to each other like that. When we react this with NH3 and heat, what do you guys think this is gonna do to this phthalic acid here? Yeah. Was it? Yeah.
It deprotonates the
Uh-huh.
hydroxy group
Uh-huh.
and then form pearl.
Uh-huh. So it would deprotonate it, but then later on, eventually, like if we have enough heat, imagine this is a carboxylic acid right here. If we substitute this OH with a NH2, what kind of derivative would that be? Would it be an acyl halide, anhydride, ester, amide? Amide, right, amide. And because we have 2 carboxylic acids in this orientation to each other, we're going to make a cyclic amide, right? Which is going to give us this phthalimide here, right? This benzene with this phthalimide right there, like this, where this nitrogen here has a hydrogen and it's neutral, right? This is a cyclic amide now, right? Because we have a carbonyl here connected by that NH right there. Yeah.
Do you feel like the mechanism is necessary?
The mechanism is not necessary for this reaction, no, yeah. But this mechanism was covered in chapter 19 and 20, like the beginning, midterm 1, right? With the carboxylic acid derivatives, like converting carboxylic acids to esters, with the proton transfer steps, peptide, like deprotonate the group you want to like keep, protonate the group you want to kick out, like all those steps right there, right? Now, this hydrogen right here is acidic, right? And the reason why is because when we deprotonate this, what charge would the nitrogen have here? When we negative charge, and this negative charge is stable. Can you guys think of any reason why this negative charge is stable? What can it do? Yeah, resonance. It can do resonance with 2 carbonyls. That's why this hydrogen is acidic. So when we put in a base like K2CO3, that's going to deprotonate that hydrogen, giving this nitrogen here a negative charge. That is stable. Right. That's good. Which is going to be our nucleophile. Right. Now, once we have this nucleophile here, we have to put in this specific reagent for this Gabriel synthesis route, right? Which is a malonic ester. So we're gonna put this ester, that ester, and a bromine right here, right? So we have 2 esters here. One ester here on the left, one ester here on the right, and a bromine at the alpha carbon. This bromine at the alpha carbon is going to be the electrophile, making this the good leaving group, right? So we're gonna do SN2 reaction here. This N minus charge is going to nucleophile that's going to go around to attack that carbon and kick out the bromine for SN2 reaction, right? So as a result, we're going to get this intermediate here. Where this is the nitrogen, and if I were to star the nucleophile, this nitrogen, that's the star, and this is the dot electrophile. This is the star nitrogen. This is the dot electrophile. This is the new bond between them, right? The bromine is no longer there, but that dot carbon right here is attached to 2 esters still. This ester, that ester, which are these 2 esters here, that ester and that ester right there, right? Yeah. Uh-huh. Yes. We do need the wait, actually, let me think of a reason why we could not just use that. Bromine, H2O plus, H3O. So if you do that, yeah. Sorry, what was the question? Sorry. Yeah.
Things like with malonic ester synthesis, you can like change those end ethyl groups to any R group, as long as there's like an oxygen there.
Yeah, like this OR group here,
Yeah.
it could be any OR group.
Okay.
It could be propyl, butyl, or something like that, right? And the reason why we need two esters is because once I have these two esters here, that would make this hydrogen here acidic, right? Because when we deprotonate this hydrogen, we're gonna have a negative charge here, which is able to do resonance with these two carbonyls right there. So that's why two esters would increase the acidity of that alpha hydrogen right there, right? So before we go over the next step, I'm going to show you guys where the amino acid is going to be at. This is going to be the carboxylic acid group. This is going to be the amino group, and that's going to be the alpha carbon group, right? So this right here, the ester, is eventually going to become the carboxylic acid group. This is the alpha carbon. This is eventually going to be the NH2 amino group. And this alpha carbon here, we could add whatever R group we want, like ethyl, methyl, isopropyl group to it. But to do that, we have to make this alpha carbon negatively charged. To make it negatively charged, we have to deprotonate it using a base like K2CO3, right? Which is going to grab that hydrogen and give that alpha carbon a negative charge, right? Okay. Now, once we have this negative charge on the alpha carbon, that's the nucleophile. And now we could bring in any electrophile we want. Let's say this isopropyl here, where this is the electrophile, this is the nucleophile. That's going to attack that electrophile, kick out the leaving group bromine, SN2, right? And that's going to give us this intermediate here. Where if this was my star carbon, this is going to be the new bond between the star and dot carbon. And this dot carbon here is attached to two methyl groups, 1, 2, which are these two methyl groups here, 1, 2 methyl groups, like that, right? And this is the new bond between them, like that, okay? Now, the next step here, when we put acid, water, and heat, that's going to do a lot of things, right? You guys notice how these here are carboxylic acid derivatives, like the amide and esters right here? When we put acid, water, and heat, what would that do to these derivatives? Carboxylic acid, hydrolysis, right? So when I revert these back to carboxylic acids, right, this is going to be the carboxylic acid, that's going to be the carboxylic acid, and these are the leaving groups. So the side product here is going to look like this. Right. OH plus right, where these two alcohols here, the two ROHs, are going to come from these two alcohols here, right, the two ROHs. This phthalic acid came from that group right there when we hydrolyzed this amide to go back to the carboxylic acid. This amino group here is now this amino group here, but the reason why this NH2 is protonated to NH3 plus is because we are still in acidic conditions, H3O plus, water, and heat, right? These two carboxylic acids here came from these two esters here. But this is not our final answer. This is just an intermediate because there's a sneaky reaction here, right? You guys notice this heat right here, the delta symbol? And let's say we look at this carboxylic acid, this is the alpha carbon. This is the beta carbon. When you have a beta carbonyl acid reacting with heat, do you guys know what sneaky reaction that would do? Decarboxylation. Yes, decarboxylation. And how would you predict a product for decarboxylation? Like what do you do to predict product quickly? Yeah, take out this carboxylic acid to give you your final amino acid here in acidic conditions, like that, right? And this would be our amino acid here in acidic conditions. You could also see this be reactive with a base to deprotonate the carboxylic acid to get the negative charge on oxygen. But if you just left it like that, then everything would be protonated because we are still in acidic conditions right there. Yeah.
So would that make the phthalic acid a catalyst?
Yeah, you could think of the phthalic acid, or so phthalic acid wouldn't be a catalyst because it wasn't used up in the reaction. This was the reactant in the molecule that was made to convert the the phthalic acids to phthalimide. And because usually we do Gabriel synthesis with this reagent here, the phthalimide, and this diester here, right? I just showed you the phthalic acid just to show you that how we got to that phthalimide, right? Yeah, so don't give that as the catalyst. Yeah, it does get reformed as the reactant, but we could have gotten this as well. We could have started from here as well, which would make this, but we didn't have that before if we didn't start off with the phthalic acid. Yeah. Uh-huh. Bromo isopropyl is what I added as the R group. That's right, which is right here. This bromo isopropyl is that R group right here. This R group that got added onto the amino acid, which is the R group of the product amino acid right there, right here. Yeah, and this is valine, VAL, right? Yeah.
Does this only work with carbon change as substituents rather than like anything polar, like a alcohol group?
Yeah, it works best with like carbon chain substituents because if we had like polar bonds or acidic or basic bonds, then there could be some acid-base reactions going on and something like that. So it works best with hydrocarbon chains. Right. Mm-hmm.
This one's valine.
This right here is valine. Yeah, when you see an R group that's an isopropyl, that is valine, VAL or V. Right. Does Fahrenheit make you memorize all the? No.
I don't think so.
Because I saw in her lecture slides, she says like you have to know, memorize them, like the 20 amino acids names, 3-letter code, 1-letter code. Oh my god, dang, that's crazy.
Just like
So
this one or two.
I know, it is.
potential test question would be something like, they give all of this, but they don't give heat,
Uh-huh.
and then so the amino acid wouldn't work.
Yeah, they give all of this, but they don't give heat. So the amino acid, if they don't give heat, then you stop here. Yeah, you can have that, right? And I'm gonna give you guys a practice problem on these 3 routes. After I give you the third one, Strecker synthesis, right? Which is the one that I gave you, Kaylee. The 3, yeah, right. Strecker synthesis. Okay. But I think you could assume that this would be negatively charged at physiological pH, right? 7.2 to 7.4, because the normal amino acid would be protonated at the amino part and deprotonated at the carboxylic acid part, right? So if I have this, yeah, okay. Okay. Yeah. Yeah, when we get to the DCC coupling protecting groups at the carboxyl group and deprotecting it and Edmond degradation, that's gonna be a little bit more biochem heavy. Right. Have you guys taken biochem yet, or are you guys gonna take it like next quarter soon? Next quarter? Oh yeah. Are they taking it right now? Yeah. Dang. Yeah. Okay. Yeah. So Strecker synthesis. So there's gonna be three reactions to the Strecker synthesis. The first one is imine formation. Second one is gonna be uh, quotation mark cyanohydrin formation, because it's not exactly cyanohydrin. I'll show you why. Cyanohydrin formation. Third one here is going to be hydrolysis of nitrile. Okay, so if I start with this aldehyde here, which is the reactant of Strecker synthesis, and I give you these three reagents here. First step, ammonia in trace or dilute amount of acid. Second step, HCN, KCN. Third step, H3O plus, water, heat. So the first two reactions are going to be from 118B. Right? Do you guys remember 118B reactions? No. Uh, so we have a carbonyl here, carbon double bond oxygen. If we react that with NH3 in trace acid, that's going to form an imine with an I, right? A carbon double bond nitrogen. And because this is NH3, this nitrogen here is going to be bonded to a hydrogen and neutral, right? I don't think he'll ask you the mechanism of it, but it's going to be very similar to like the carboxylic acid mechanisms, right? Like this will just convert the carbonyl into the imine with an I, carbon double bond nitrogen, like that, right? The HCN, KCN here, HCN, KCN is going to create this cyanohydrid looking like structure here, where the NH2 is going to come from this imine, and then the CN is coming from the KCN, HCN, right? I'm just going to give you guys the reactions here, and then can go over mechanisms afterwards. But when we have this nitrile here, which is a carboxylic acid derivative, we can hydrolyze it using acid, water, and heat to convert that nitrile into a carboxylic acid, right? Giving us our amino acid here.
And then once again, it's positive because it's in acidic.
Yeah, this NH3 is positive because it's in acidic conditions, and we're going to assume that this gets deprotonated because we're on physiological pH. We just get to the physiological pH amino acid, right? And the R group is already preset given to us, just like the first reaction we did, the HBZ reaction. Yeah.
Just for whenever we have synthesis questions like this, where we end with the product of amino acid, is it safer to always just put it in this Zwitter ion configuration? Or
Yeah, it's safe to put it in Zwitter ion configuration. That's what I've noticed for Farhat's class. But for Levin's class, she's very specific on like the acidic and basic conditions. So if it's in acidic conditions, then Levin's would want everything protonated, right? And then to get to this part, you have to put some kind of base like K2CO3 to get to this part. But for Farhat, just assume Zwitter ion amino acid. Yeah. Uh-huh. Yeah.
Protonated amino group and a deprotonated acid.
Yes, protonated amino group, deprotonated carboxylic acid group for normal physiological pH amino acid. Right. Okay. Yeah.
So then, how would we get anything that isn't like a carbon chain as our group?
Oh, like thiol, acidic R groups.
Yeah, or is that important? You think?
I don't think so. I don't think so. Yeah, I don't think it resistance. But I like that question though. Yeah, because if you already start off with the acidic or basic R group, right? Then this trace acid and amine group can react with that R group side chain. But in most problems, you probably get is like an R group that is hydrocarbon chain, non-polar, non-acidic, non-basic, for these three reactions: HBZ, Gabriel, and Strecker synthesis. Right. Uh-huh. So I'm gonna give you guys a practice problem using these three synthesis routes we just did. Okay. But and before that, do you guys want to go over any mechanism of from here to here or from here to here or from here to here? I don't think so. You just have to know like the step-by-step process of structure synthesis. Yeah, product by each step. Where the reactant is the aldehyde, and when you see these three reactions to this aldehyde, you're gonna make the amino acid, right? And to predict the product quickly, you could say that this carbonyl-carbon of the aldehyde is going to be that alpha carbon of the amino acid right there, right? And this carboxylic acid carbon is the nitrile carbon right there, right? And then the amine nitrogen comes from this ammonia nitrogen right there from the mechanism, right? Yeah. So when you see aldehyde reacting with these three reagents, convert that carbonyl-carbon of the aldehyde to the alpha carbon of the amino acid. So just put like an amino group and carboxylic acid to it to predict the product quickly. Yeah. Mm-hmm. Yeah. 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 Question? Uh-huh. Oh, how this carboxylic acid is deprotonated and the amino group is protonated. So we just assumed that we put some base like KTOCO3 to deprotonate the carboxylic acid to carboxylate, right? But in acidic conditions for leavings, as it is right now, everything should be protonated. Like this carboxylic acid should be neutral with the OH, right? But for Fahrenheit, you just assume the Zwitter ion form. You assume that the carboxylic acid gets deprotonated. Yeah. Because this is the normal amino acid at normal conditions, physiological pH, where the amino group is positive charge and the carboxyl group is negative charge. Yeah. Uh-huh. Yeah. Yeah.
How do you join two amino acids together? Or
Yeah. Join two amino acids together. That's gonna be with DCC coupling and protecting groups with Bach protecting group, CBZ protecting group. We'll go over that after this problem here. Because and while you guys work through that, I'm gonna read through the notes here because that's what I'm a little bit iffy on. Yeah. Uh-huh. Okay. Any other questions on these three? Okay. Let's go here. Okay. So this is just a synthesis type of problem. I want you guys to synthesize. And since you guys have to know the amino acids, names, 3-letter code, and 1-letter code, I'm going to write the 3-letter code of the amino acid. Synthesize. Wait, let me make sure this is right. Yeah, it's right. It's right. Okay. Synthesize that amino acid. Um, Starting with a molecule that has no nitrogen atoms, right? And I want you guys to use 3 of the reactions we just did. HVZ route. The hardest one, in my opinion, is the Gabriel route, Gabriel synthesis route. Like, there's so much going on there. Gabriel, and then the last one, Strecker. Strecker. Okay. While you guys go through that, I'm gonna reveal the other stuff. Yeah. Oh, hey, Alessandra. Yeah. Excuse me. Thank you. Hi. Hi. Hey, Alessandra. Here's your hoodie. Yes. Uh-huh.
So cool. Did Annie leave?
Yeah, Annie was just here, like earlier. Yeah.
Oh, this is her. Was this her?
Oh yeah, that's her. That's her.
I yelled her name, but she didn't turn around.
Oh
I
my
didn't want,
god.
I didn't want to like come up to a stranger. So
Yeah.
I wasn't sure.
You should send it to her. It's like I saw you.
I did.
Oh, are you gonna stay here until the end of the session? Yeah. Okay. Can we take like a selfie picture with us afterwards? Okay. Okay.
Or okay.
Yeah. After the session. Yeah. Uh-huh. Session. Yeah. Yeah. Kathy, you have my phone.
For this one,
Mhm.
for the reductor
Amination.
animation, like I kind of started it, but like
Right.
I'm not really sure if this is like right.
And H3, convert that into the E-mean, H2 PDC, convert that into that. Yep, that's right.
Okay.
Yeah,
And
you
then
got it.
for like the striker
Uh-huh.
synthesis, I'm still kind of confused. Like, did we use HVZ and 8B on the Gabriel one?
Yeah, HVZ we went over. Gabriel is the one with the N-phthalimidyl malonic acid synthesis. That's that
This
one.
one?
That's the Gabriel. Yeah.
Oh, okay.
Uh-huh. Right. And Striker is that one. Yeah.
Yeah, the striker synthesis.
Uh-huh. Right. Uh-huh. Yeah. Uh-huh.
These are actually similar.
Right. So wait, let me see.
Did it both ways.
Both ways, right?
Striker and then HPZ.
Uh-huh. Right. You did Striker, ACN, TCN, H3O plus. Yeah, that's right.
Okay.
And this one, yeah, yeah, and
Okay.
NH3. Yeah.
Yeah.
Yeah,
Okay.
you got it. Yeah, yeah, yeah.
Okay.
Uh-huh. Nice.
The other Gabriel uses the actually.
Mhm.
Gabriel. Okay.
Yeah.
We could drop into
Yeah. Uh-huh. Right. Okay. But in Gabriel, I would start. You can start here,
Mhm.
right? Or you can start off with here,
Okay.
with that group, and then as the reagent, you could put um, this phthalimide as the reagent as the first step to be quicker. Yeah. Uh-huh.
I guess everything with Gabriel synthesis is like the same starting product.
Mm-hmm. Yeah, everything with Gabriel synthesis is the same starting product. The only difference is the OR group you put in. Like once you get that like tetrahedral intermediate with the negative charge alpha carbon, you put in any OR group you want.
I see.
Yeah.
Sorry. Right.
Uh-huh.
The naphthalate acid, they use
Yeah.
this as the
The reagent.
reagent.
Yeah,
Right.
you could start that as the reagent. Yeah. Okay. So let's go. Naming peptides.
Yeah, my phone's gonna die. So yeah, so this is what you want. So I started with that R group. It's endlessly 4 days and 25 degrees Celsius. But you said it's like, you know, that's negligible. But that's what you got, right? There's just like mine. Yeah, it's 4 days. It's not 25 degrees Celsius.
Right, I have a question.
Yeah.
Just like general questions, so I'm not getting one answer.
Mhm.
Malonic acid synthesis, like with the Gibson,
Okay.
is it two equivalents of the potassium carbonate?
Two equivalents. Yeah, the first equivalent would be used to deprotonate the phthalimide to make the nucleophile. The second equivalent would deprotonate the alpha carbon to make that nucleophile. Yeah, you get to give us two equivalents. Yeah, yeah.
So funny because I was asking the same thing
Oh wait, no.
earlier. He
Oh.
does. He does. Because that's the one I need. He had the one I didn't need, which is your charger. Thank you so much. Do you have an iPhone charger? No. Does anyone have an iPhone charger? An old iPhone? Yeah. Because I would plug it into my laptop. And it would charge.
Does it start
Uh-huh.
with phthalic acid or
Mm-hmm. Yeah, so there's multiple starting points. You can start at the phthalic acid, or you can start at the um, not the phthalimide because that has a nitrogen, and we don't want to start with any nitrogen atom. But we can start with the beta diester, the two esters with the bromine in the middle as a reactant, and then the reagent, the first reagent, could be the phthalimide that's deprotonated, right? So if you have your notes for the uh,
is the notes for the groups?
Gibson, you can start with this reactant here, the two esters with the bromine,
the thing.
and then the first reagent you could have is this right here. That could be your first step reagent.
So
To
it's
get
a
to
reagent,
here.
not a reactant.
Yeah.
Okay, so it's like
Switched.
manipulating.
Right, right. Uh-huh. Shit. Okay, so my iPad is about to die, so the recording might be cut a little bit short for 1:16, if that's fine, or we could use like some. I don't know. I don't know how. Yeah. Uh-huh. Let's see.
Did you say for Strecker that the R
Uh-huh.
group is already going to be on the molecule? Or is that.
The Strecker, the R group is already on the molecule, right?
Okay.
And the R group is the aldehyde R group,
Mhm,
right?
Okay.
Uh-huh. Same as for the HVZ, the R group is already on the molecule, but for the Gabriel synthesis, you get to choose what R group you want.
Okay.
Yeah, you bring that in.
Okay.
Uh-huh.
So like you would have the R group of islands.
For the Gabriel synthesis, yeah, the R group would be the electrophile for Gabriel synthesis, right? You bring it in as the electrophile. Right. Right. Yeah.
I believe like before I learned that like the base has to match like sort of the
Mm-hmm, mm-hmm.
what is it like the esters?
Oh, right. Yeah, that's a good point. Oh my god. So for Gabriel synthesis, right? When we get to this intermediate right here, which is the like that, where we said that this hydrogen was acidic, right here. The base that we use has to be the same OR group as the ester, right? If the ester here is an O, like ethoxy group, our base has to be this ethoxide ion. So you have to use NaOR group where the OR group matches the OR group of the ester, like that, right? And that would deprotonate this alpha carbon to give that alpha carbon a negative charge. The reason why we cannot use OH minus is because OH minus would do hydrolysis to all these derivatives. It would hydrolyze the ester, and amides into the carboxylic acids, right? So that's why we don't want to use hydroxide ion because that's going to do hydrolysis, hydrolyze the carboxylic acid derivatives back into the carboxylic acid, but we don't want that. Yep.
So would something like I don't know NaOCH2CH3 work for?
Uh huh. Yeah. NaOCH2CH3 would work to deprotonate this alpha carbon right here.
So it's not two equivalent.
Yeah, so it's not two equivalents of K2CO3. The first equivalent of K2CO3 deprotonates the phthalimide. The base needed to deprotonate this alpha hydrogen here is going to be the OR minus group that matches the OR minus of the ester here, right? And the reason why we can't use a different OR minus where the R group is different is because that would do a different reaction. What reaction would this do with this ester here? Trans esterification, right? It's going to convert this ester into a different OR group, where the OR group is going to be the OR group we use as a base. Trans esterification, right? But we don't want trans esterification. We don't want hydrolysis. We want to deprotonate the alpha carbon. And to do that, we have to use the base that matches the OR group of the ester. Right. Right. Yeah. Yeah. OH minus would do hydrolysis. A different OR prime would do trans esterification, converting these esters to a different ester. So that's why we have to use the OR minus that matches the OR of the esters to deprotonate the alpha carbon here. Yeah. All right, that's a good one. Okay. protecting group, CBZ, Buck.
Is this like the longest reaction, or is Gabriel is the longest reaction of 26?
For 26, the longest reaction, yeah, for 26. Gabriel synthesis.
Oh yeah. You got like
Buck.
yeah.
Okay. To protect this.
No, my I use it to charge my phone and my for your iPhone. It was. It was. I charged my. I charged everything at the same time.
Open it. We don't know.
Okay. Yeah.
So, for you said the base should be equivalent to
Mhm.
the ester group.
Yeah, the OR has to be equivalent to the
Why
base.
for this one?
Yeah, I messed up here. Yeah,
Oh,
it should be OR minus, where the OR minus is that OR of the ester.
so it's always gonna be this.
Yes. Yes. Uh-huh.
And then do we add the R group?
Um, let's see. The R group. Yeah, so once we deprotonate this alpha hydrogen, that carbon will have a negative charge, and then that negative charge will attack the carbon, kicking out the bromine, and then the R group would be attached on that carbon. Yeah.
And then what do we do next?
And then from here, right, this is where you do acid, water, and heat, hydrolysis, and then decarboxylation, right?
It will cleave.
It will cleave this side off, make these into carboxylic acids, and then get rid of one of the carboxylic acids to get the amino acid. Yeah. So once we get this part right here, with the two carboxylic acids, one of the carboxylic acids will disappear because of decarboxylation
By using acid
and heat. Yeah.
wait, what about
Uh-huh.
the NH?
The NH3 is the leaving group of the amide here. So you know how we had an amide here, right? When we put acid, water, and heat, we're going to convert these amides into carboxylic acids. So, and this N right here is the leaving group that leaves, and that's going to be NH2, but we put it as NH3 plus because we're in acidic conditions. So when we go back to here, right, these should be carboxylic acids. They should be OH and OH.
Oh, this is OH.
Yep, OH. Right. Carboxylic acids. Because we're converting the amides into carboxylic acids. Yeah.
And so the rest of the steps before you attack like the alkyl group is always the same steps, and then it's just the R group.
It's just our group that's different. Right. Yep.
Hydrolysis first.
Yeah, no worries. Yeah.
For Gabriel, do we need a non like? Do we? You were using a different base.
Oh yeah, K2CO3,
Yeah,
NaOH would work as well.
Okay.
Right.
And then I think that would.
Yeah.
Should we do the same base that we used to remove the alpha hydrogen the second time,
Ye-
like twice?
The OR minus.
Yeah.
Yeah, you could use the OR minus to deprotonate the phthalamide as well.
So I didn't want to remember like two separate reagents on the thing.
Yeah, the same reagent. Oh, we will start. I'll probably answer her question, and we could like start going over these questions here. Or did you have to go somewhere? Or
I just wanted to go to the bathroom, so I just wanted to see.
oh yeah. Okay. Yeah, I could wait until you like come back or something. Yeah. Yeah. Uh-huh.
Is that right? And I'm not sure, like, and you just add, like,
Mhm.
change there, right?
Yeah. That's right.
And like, wait, here you don't
Uh-huh.
need the decarbonation.
Uh-huh.
You don't need a heat here.
You could go from here to here.
with the heat. Okay.
You put here right there.
And also, like, when you were explaining Gravell synthesis,
Mhm.
you use like K2CO3 to deprotonate.
Yeah,
it,
that
so-
was a typo. That was a mistake.
typo? Okay.
Yeah, that was a mistake. Yeah.
But here it doesn't matter.
Yeah, it
right?
doesn't matter.
Okay.
Right. But this one here should be the OR that matches that
Okay.
OR of the Gabriel synthesis right there.
And I just for like Sticker and HBZ. I just started with that part and
Uh-huh.
just went over it.
Yeah, right.
It
This one
doesn't matter if
imine.
you like have a long carbon chain, right?
Yeah, it
Yeah,
doesn't
that's
matter.
it.
It still works. Yeah, you got it. Yeah, yeah, I did it. Yeah. Uh-huh.
Sorry, I couldn't
Uh-huh.
see the board at the bottom.
Oh
Can
yeah.
you explain like what
Uh-huh.
you did?
hmm
Because I could see up to here,
Right, right.
and then like a
There was
line there.
a typo here that I made.
Yeah, the transistor fusion. That's fine.
Yeah, this one here, the hydrogen.
Yeah.
We don't use KTSO3 to deprotonate that hydrogen.
Okay, we're gonna
Right.
use like a
OR
okay.
minus, right? And the OR minus has to match the OR of the ester right there.
Okay.
Right. So the Gabriel synthesis, you can start with this phthalic acid, the benzene with two carboxylic
Yeah.
acids. We reacted with amine ammonia, and the heat to create this phthalimide, the amide. Right. We're merging these two together to merge it to the nitrogen of the amine right here.
Yeah.
Right, to create the phthalimide. And this is acidic because when we deprotonate it, it will have a negative charge that can do resonance with two carbonyls. And
Okay.
the base we use to deprotonate it is K2CO3. Right, and this is the nucleophile that's going to be used to attack this two esters here with that bromine in the leaving, like in the alpha carbon, and that's always going to be there for Gabriel synthesis when we create
There will
amino
always
acids.
be a bromine,
Uh,
or
good
just
leaving
a
group, good leaving group,
Okay.
right? Like chlorine,
Yeah.
OMS, OTS,
Mhm.
but you have two esters and a good leaving group, usually bromine.
Okay.
And when we do that, we're going to have this structure right here, the intermediate of Gabriel synthesis.
Yeah.
Right, so everything is going to be the same up until this point, right? Because the next point it's going to add whatever R group we want to put into it, right? Because this hydrogen here that is the alpha carbon between the esters and the amide
Yeah.
is very acidic.
Yeah.
Right, so when we deprotonate that using the OR minus of the ester, we get a negative charge there, right? And then from
Yeah.
here you get to choose whatever R group you want right here, depending on what amino
Okay.
acid you want. But if you want isoleucine, which is that one, you have to use the R group of the isoleucine as for SN2 right there. Right, and that would add the R group right here on the alpha carbon, right? And this R group is variable. You get to choose what that is depending on
Okay.
what amino acid you want. And then from here you just do hydrolysis, which was gonna hydrolyze these amide, like the cyclic amide and esters, into the carboxylic acids, right? And
Is
you know
that
how
just,
this
like the dehydration thing?
yeah, dehydration thing. So it's hydrolysis. Think of it as
Oh.
hydrolysis, yeah. Because these esters here are converting into alcohols.
Yeah, that's.
I mean carboxylic acids,
Mm.
kicking out that alcohol right there.
Yeah.
These amides here are converting into the carboxylic acid, kicking out that amine group right there.
Oh, so we take out the nitrogen.
Yeah,
and
we
add-
take out
Okay.
right. If I add OHs here, the carboxylic acid, right? And then once we have the two carboxylic acids here, beta to each other, the heat would get rid of one of the carboxylic acids for
Okay.
decarboxylation, giving us this amino acid. But usually they're going to assume negative charge on the carboxylic acid. Like they're going to assume that that oxygen there is
That's the
negative charge.
ion thing that you
This is what the ion,
Okay.
right? Uh-huh.
Okay. I have to practice this one.
Yeah.
This one is weird.
Yeah, this is the chapter 19 reaction hydrolysis, chapter 19. But the decarboxylation is a new one, chapter 23.
So we're basically breaking it.
Yeah.
And creating two.
We're
Okay.
breaking like 4 bonds. We're breaking that bond, break that bond, that bond, and that bond.
Okay.
Yeah.
Okay.
Uh-huh.
Thank you.
Yeah. Uh-huh.
For the art
Yeah.
group, is
Uh-huh.
it always going to be bonded to like a bromine?
Uh,
Or just like any group?
any leaving group, good
Okay,
leaving group.
doesn't
Yeah.
really matter
Doesn't
what it is.
matter. Yeah.
Okay.
Mhm.
And then my other question was for proline, because it's cyclic, does it still have stereochemistry?
Oh, for proline as the
Yeah.
R group,
Yeah. Because it's like
Uh-huh.
urine.
one group attached to the amino acid. So that's gonna be
Yeah.
harder because like proline, the R group is attached to the amino group as well. So we
Right.
can't make proline from these
No.
synthesis.
Okay.
Yeah.
Okay, cool.
Yeah. Uh-huh. Did you take biochem? Yeah, this one or two.
Mhm.
Oh yeah, that's
Taking
how
it
you know.
right
Yeah,
now.
proline. Yeah.
Yeah.
Yeah. Did you already memorize the 3-letter codes and names?
I
Letter,
did for
one
our
letter
last
code.
midterm, and I'm like, I hope it doesn't fail me right now.
Oh yeah.
It's gonna be really hard to remember.
I know.
No offense.
Yeah. I see. Yeah. No, no worries. Uh-huh.
The base be the same or
Okay. Okay. So HVZ, Hell-Bohr-Zelinsky reaction. If we want to make isoleucine with this, we want to start with a molecule that has no nitrogens. So what was HVZ again? It was the carboxylic acid, right? And then we add the with an alpha carbon. So let's say we have this carboxylic acid here, and that's going to be the alpha carbon. This is going to be the carbonyl carbon. This is the alpha carbon. And we know that eventually, when we do HBZ, the alpha carbon is going to have the amino group, right? So whatever is coming out of that alpha carbon is going to be our R group. And is this the R group of isoleucine right here? One carbon short.
No, I mean like
On the tail, right here.
Yes.
Oh, like one more carbon?
No.
Oh, one less carbon, like this. Oh, okay, like this, yeah. Right, I think?
I think so.
Yeah, okay. Yeah. So this right here is the R group of isoleucine that we want to make. HVZ is going to add a bromine to the alpha carbon. So we're going to do Br2, PBr3 trace to add a bromine. Alpha to the carboxylic acid right there. Right. Now, the next step is just to put like NH3 to convert the bromine into NH3 plus and deprotonate the carboxylic acid to carboxylate, creating our isoleucine there, right? And this works because our reactant here has no nitrogen atoms, so that's good, right? Okay. Yeah.
This is just like a really like technical question.
Uh-huh.
When I was looking at the stuff from Mariah's, she also said like I earlier you said 25 degrees Celsius. You could also just put room temperature, right?
Room temperature, yeah.
And then she said 3 days. So can
3
we
days.
technically just put 3 to 4 days?
3 to 4 days,
Something
yeah.
like that?
Yeah, you can put something like that for synthesis. But I feel like this is gonna be more
Specific,
on
much more specific, you think?
for not for Farhat, like Farhat, I don't think like he cares. You can put like 3 or 4 days, doesn't matter for synthesis. I feel like this is gonna be more for multiple choice questions. I think feel like you're gonna see it as a multiple choice question for
I see.
Farhat.
Okay.
Yeah.
Yeah, because it's a pretty quick.
Yeah.
I see.
Would we
Right,
find
uh-huh.
the first solvent or first reagent, like for example, would like sorry, the BR2 PBr3
Yeah.
trace? Would we find like the PBr3 trace just as like trace BR and it would be the same thing?
Trace BR2.
Yeah.
If you have BR2, there's another reagent for HVZ. I remember it was something without the yeah, it was like the no, yeah, it's something with phosphorus.
Oh, phosphorus.
Phosphorus, yeah.
Oh, trace
Yeah,
trace
Morales had
Or
trace
PC,
P.
Trace.
PCO5 maybe?
I just have like trace P.
Trace
It
P,
is trace P, yeah.
and then just BR2. Yeah, but eventually these will combine to make PBr3. Yeah, which is trace. Yeah, so if you see BR2 P trace or BR2 PBr3 trace, they'll do the same thing. HBZ. Yeah. Okay. Next one, Gabriel synthesis. Okay. Which is the longest one? Right. Gabriel synthesis. So I'm gonna do it in the way that I taught you guys, which is the starting from the 2 carboxylic acids, right? But there is a shorter way that you can start off with, right? How can we convert this into the phthalimide? NH3 heat, right? And the reason why we need heat is because carboxylic acid is one of the lower reactive derivatives, right? Do you guys remember the top 2 most reactive derivatives that does not require heat? Anhydride and acylchloride or acyl-halide, acyl-bromide, right? Anything below that, like carboxylic acid, ester, amide, will require heat to do the reaction, right? That's gonna make this phthalimide here. And then once we have this phthalimide, what base can we use to deprotonate this phthalimide? There's a lot of bases that we could use. Yep, K2CO3, right? NaOH can work as well, or NaOH, or OR minus, like any strong base, to deprotonate that phthalimide to get this negative charge here, the nucleophile, right? Now, this is the ester, diester that you have to remember, where at the alpha carbon, there's going to be a bromine between them, which is our electrophile right there, right? For SN2 reaction, that nitrogen is going to attack that carbon, kick out the bromine, to give us this intermediate here. So all Gabriel synthesis will be the same up until we choose our R group, right? The R group of the amino acid.
You said we could also start at that one, yes?
Yeah, we could also start right here where this is the reagent, but I just started here just to show the more full synthesis, but I'll show it this way later.
Would you do that one with like can you just react it with N minus like that,
Mhm.
or
Yeah,
have to be like N like with the
Mhm.
like K or I don't know.
right. It could be like NK or like NaN,
Yeah.
right? But this can be the reactant because the instruction says that we cannot start with the molecule without nitrogens. So you would have to start with here, and then on the arrow you could bring this in. Yeah.
But like in the test, if we started
Uh-huh.
with the diester, then you would react that with like
With
Na
this.
and
NaN and that whole thing right there. Yeah, you could do that. Yeah. Right. And that's gonna be this. Right. And this acidic hydrogen here, what base do we have? What specific base do we have to use to deprotonate that alpha hydrogen? Yeah. 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 Where the OR has to match the OR of the ester, NaOCH2CH3. Or you could draw that like this, which is going to grab that hydrogen and give that carbon a negative charge. The nucleophile. Right. Okay. Now, once we have this negative charge nucleophile, this is the point where Gabriel synthesis will be different for all amino acids, because this is the point where we get to choose what our R group is, right? So our R group that we want is isoleucine. So we're gonna have something like this, right? I think as the R group, if we want to add that isoleucine in. The OR minus has to match the ester tails. Yes, the base that we use has to match the ester tails.
but that one doesn't.
Yeah, the R here doesn't have to match the ester tails. This could be variable. It could be ethyl, methyl, isopropyl, sec-butyl, something like this, which is gonna attach onto this alpha carbon right here, kicking out that leaving group to give us this intermediate here. Nitrogen. Right. This is a star. Dot is attached to methyl and ethyl. Okay. Now the last step is going to do a lot of things. It's going to do hydrolysis of all the derivatives, which is going to cut 4 bonds. Going to cut this bond, this one, and this bond to create the carboxylic acids and its leaving groups, and then do decarboxylation to get rid of one of the carboxylic acids to give us this amino acid here. Right. H2O plus, water. This is probably the most confusing part of Gabriel synthesis, like this step right here, right? Because if you were to draw out the mechanism step by step, arrow by arrow, it's gonna require like 2 pages or 3 pages. Because you have to do hydrolysis of this amide, that ester, and then the decarboxylation mechanism, right? So that's gonna give you plus minus like that. You can draw the intermediate if you want, which is going to be this. With 2 carboxylic acids and the side products as well, which is going to be this phthalic acid and the 2 alcohols that left. Yeah. Can you guys? Yeah. Right. Okay.
So the breaks are what leaves.
The breaks here are what leaves, yeah, because this would leave as this phthalic acid, carboxylic acid. Because if you think about this, what is this functional group here? A carbonyl attached to NR. amide, right? And when we hydrolyze any derivative like amide ester, anhydride, acyl halide, we are going to convert it back to the carboxylic acid. So when we convert this back into the carboxylic acid, this N here is the leaving group that leaves. But this ester here, the carboxylic acids are still a part of this amino acid. But the leaving group that leaves are these two alcohols here, right? And then from here, we just do the sneaky step of decarboxylation to get rid of one of the carboxylic acids, like that. Right. Okay, Strecker synthesis. Okay. I want to go over the DCC, Bach, and CBZ and benzoic ether reaction before we end the session, because that one's like probably like one of the most important ones. Right. Yeah. Okay. So Strecker synthesis. What did you guys start off with if we want to create isoleucine as a reactant? Aldehyde? Yeah, with the isoleucine thing, like this?
Yeah.
Yeah, okay.
No, wait, isn't it? It has to at the next part, right? Or at the next carbon,
Yeah, like that's not the alpha.
the methyl.
Mhm.
Methyl goes on that
This
one,
carbon.
and then there's one more.
Oh, no, I think it's like this because this carbon here of the aldehyde is going to be the alpha carbon of the carboxylic acid, right? So if that's the alpha carbon of the amino acid.
Oh, zero.
No, only
Yeah, thank you.
Zero.
Oh, screen recording? Okay. Yeah, thank you.
So only Strecker and HVZ start out with a desired R group.
Strecker and HVG only starts up with the desired R group, and Gabriel, you get to choose your R group with that electric pile.
Why if we just have
Oh, ACN? You don't need KCN because when we protonate the carbonyl, we kick out ACN minus, and then we can use ACN minus to attack. So you don't need KCN. Yeah, you just need ACN.
It's just better than like
Some subtype.
actually.
Yeah, I just put KCN there because that shows that there's other CN minuses floating around, and that's how like Mystery taught me. So I was used to that that way. Yeah. Okay. Okay. So are you guys ready for how to like form peptides?
Oh yeah, peptide bond.
Peptide bond formation. Yeah. Let's do that. Okay. DCC. Okay.
Whenever I work with people, we like we have like a good 20 minutes of working on our own and like updating each other. Sometimes we can play off.
So before we go over that, let's explain what the peptide is. Let's say we have this amino acid. This amino acid here. I'm gonna make it neutral. Actually, I'm gonna make everything neutral for now. But note that at physiological pH, the amino group is positive, the carboxylic acid is negative. Q OH dash R. This is R1, this is R2. So this is going to be my amino acid 1. This is going to be my amino acid 2 with 2 different R groups. We can merge these amino acids together to make a peptide bond, right? And if we have a lot of amino acids string together, that's going to be the primary structure of a protein, the sequence of amino acids, right? So, let's just say that we react that with heat, which is going to combine this carboxylic acid and this amine together to create what kind of functional group? Think back to chapter 19 or 20. Amide, right? where when we do that, we're gonna get this here. Nitrogen H OH R2. This is the new bond that we formed between this carbon to carbon and this nitrogen right here. If this carbon to carbon was my dot, this nitrogen is going to be my spot, making this my new bond. Right? And this is a condensation reaction because we got rid of water. We see that this OH group is no longer there, and one of the hydrogens of the nitrogen is no longer there. So when we get to this product here, we get rid of a water molecule as well. Right? 2 hydrogens from here, 1 hydrogen from here. Condensation. Yeah. Yeah, that's it. This is a peptide bond right here. The amide bond, amide linkage, right? Which is the peptide bond, or you can see this referenced as amide linkage. Peptide bond, aka amide linkage. Now, if we talk about the property of this, does this peptide bond have free rotation? Can it freely rotate? No, it cannot, right? Because
There's an sp2.
yeah, this is sp2. It looks sp3 because it has 4 different groups attached to it. 1, 2, 3, 4. But the reason why it's sp2 is because it could do resonance with the carbonyl, right there, right? And when it does resonance, there's going to be a double bond here, and we cannot rotate double bonds at all, right? So that's why this is sp2, making this peptide here restricted, right? And that's good for biochemistry because in proteins, if that was able to freely rotate, everything is going to be floppy and like melting, right? But we want this peptide bond here to be able to be unrestricted, not freely rotatable, to keep the proteins rigid and stable, right? Which is due to this resonance going on here between the amine nitrogen and the carbonyl here. So instead of heat, we can use a different reagent known as DCC. And the structure of DCC would look like this, which you might see on the problems, right? The practice problems or
Is this was condensation?
The first one is
the first one is condensation for amide formation between carboxylic acid and amine, which releases water as a side product. So when you see this structure on the reagent, always associate this structure with DCC, right? And this DCC here is going to react with carboxylic acid plus amine to create some sort of amide, right? So DCC will combine carboxylic acid and amine together to form an amide. Some examples would be like this. If we have this carboxylic acid here, and we have this amine here, and we were to react those 2 molecules with DCC, we would get this amide right here.
It depends on
Or this is the new bond that was formed between them.
this guy. This guy is this guy already has why would you add
And this is going to be important when I go over the amino acid and protecting groups out there.
Could you do like a star dot thing?
Sorry, dot thing, yeah. So we can say that this is the star, nitrogen. This is the dot, carbonyl carbon. Star, nitrogen, dot, carbonyl carbon. Water also leaves. That OH leaves, one of the H's leave, and it leaves as water.
this part I included think okay I don't really want to put it alcohol in it. I'll just use this liquid here and add it's like part of the reaction. So here I
Do you know what DCC stands for?
DCC? I don't know off the top of my head. Dicyclohexylcarbodamide. Dimide, yeah. Dicyclohexyl. So two cyclohexanes,
Yeah.
dicyclohexyl, carbo, that's the cyclic thing, diimide. Two imines. Two imines. Two carbon double bond nitrogens
Okay.
to each other. This would link a carboxylic acid and amine together to create an amide. Amide function. Yeah. Let me show you the specific problem.
Yeah, HOH, which comes out as well.
Let's say we want to create this dipeptide, alanine valine. Okay, which is going to look like this right here, where this is amino acid 1, and the R group of alanine is a methyl group. That's the R group of alanine. This is amino acid 2, and the R group of valine is an isopropyl group. And this is right here. This right here is the peptide bond that connects these two amino acids together. Amino acid 1, alanine, and amino acid 2, valine. To do that, you might want to think about, let's say we have this neutral alanine here, carboxylic acid, and this that, right? You might think of combining those two amino acids using DCC, which is going to merge this carboxylic acid and this amine together to create this amide right here, right? Which will create that, right? We're merging this carboxylic acid and amine together to create that amide right there. But there's a problem here. Can you guys spot any problems with this synthesis? Like, it's gonna create other products as well.
Oh.
It
Water
can be
is a
different
byproduct.
combination, like alanine and valine, and then valine, alanine, valine.
Right. We could get valine, alanine. We could get alanine, alanine. We could get valine, valine. Right, in that sequence. Right, because the amine group of this alanine here could have merged with that carboxylic acid group of that valine. Wait, alanine here with this valine here. So if we combine those two together, this is what we would get. Right. And this right here is valine, peptide bond, alanine. Right. And we did not want that valine alanine. We want this alanine valine. But we will also get this valine alanine because the amino group of the alanine here can merge with the carboxyl group of the valine there. But there is a way for us to just get this desired product that we wanted to begin with. Right? To do that, we have to protect this amino group and protect this carboxyl group. Right? Make them unreactive. And there's 3 protecting groups. To do that, Boc, CBC, and benzoic ether. CBC, immunobacteria. Okay. So there's 2 or amino and protection. Wait, this is going to be talk about protecting groups now.
No. I didn't know.
And that's one for the carboxy. So the first one for the amino end is gonna be CBC. CBC. There's a full name for it as well, which you might have to know for Farhat, because I know Farhat likes to write the full name out for the multiple choice questions, and you have to know what that is, which is
Wait, that's kind of wild. I mean,
methoxycarbonyl group.
but that's kind of.
Methoxy.
That's kind of. That's kind of. No, I think that. I guess the right. How can you say the sun is going back?
And what that looks like is this right here.
I think I'm lucky. Yeah, we say
This is CBZ. So if we wanted to protect this amino group of the alanine, we could use CBZ. So let's say we use this protecting group. We're going to get this protected amino group here. Right. And you could abbreviate this as CBZ and CBZ only. So now this is not an amino group anymore. If you react this with this, then the amino group is blocked off because we protected it with the CBZ. Okay, so if we try to put DCC on this amino group is no longer reactive because we protected it with CBZ. Right. The other protecting group that you can see is with BOC, which looks like this here. This tributyl bulky structure here. And let's say we react with the same alanine. We're going to protect the amino group once again, but it's going to look like this. Yeah. And you could abbreviate that as BOC and carboxylic acid like that.
Next question.
Yeah.
How come there's no H on the end product?
Oh, H, oh yeah, there should be an H here. You're right. Yeah, there should be an H there. Yeah, right here. Right.
Is the buff the bottom?
Yeah, this buff is this right here. CBZ is this right here. Right. The reason why we put CBZ or BOC on the amino acid is to protect the amino group. Right. We convert the amino group NH2 into some other group that's not an amino group. And that would not react with DCC. Because when we learned about DCC combines a carboxylic acid and an amine to create an amide. If we block off the amine using CBZ or BOC, then the amino group of the group that we protected, that amino group is not gonna react with DCC at all. Right? Yeah.
How many, like an amino acid that has the group or carboxyl group, we could also do this, right?
Yeah, we should also do this as well because if there's an amino group or a carboxyl group at the R chain, like the acidic ones, glutamic acid or aspartic acid, then you would have to protect those as well, those groups as well. Yeah.
So Bach slaps that like Turk detoxy like double bond carbonyl thing.
Yeah.
But like is Bach itself the bottom left thing that you drew there?
Yeah. This right here would be Biz Bach with Bach. Let's see. Yeah, Bach specifically is this right here. That
Okay.
left side right there.
Wait, couldn't like either of those technically what's it called? Join on the end of the other amino acid?
It could, yeah, like right here. It
Yeah.
could have reacted with this one right here. And that's a good question because we're reacting this block or CBZ with this amino acid only with one flask. Right? Like one flask is gonna have this amino acid.
Oh right,
We're not gonna have that.
I see.
This is gonna be in a different flask where if we don't want this carboxylic acid to be reacted with, we have to protect that carboxylic acid with another protecting group. And then once we protected that carboxylic acid, we bring in those two flasks together to react the protected amino group and protected carboxyl group, leaving these two groups open only to create this desired amino acid group there.
I see, okay.
Right. But then later on, we have to deprotect the amino group and deprotect the carboxyl group to get to the original reactant.
Right.
Which is what I'm going to show here, like how to go backwards.
Right.
Right, how to go backwards. Right. So to go backwards here, if you use CBZ to go backwards, you want to use H2PDZ. H2PDZ or Bach. If you want to go backwards, deprotect the amino group, you're going to use the deprotecting agent HCl or CF3 COOH. That. We're just going to deprotect that Bach group back into the amino group. Okay, yeah. So, if we want to protect the carboxy group, which is the group that we want to protect at the valine, we're gonna react it with this type of alcohol, which is benzylic alcohol. Okay. Do you guys know why this is the benzylic alcohol? Here.
Because there's an alcohol connection.
On the
carbon.
benzylic carbon, right? At the benzylic position. If we react that with acid, right? What is this gonna do? Chapter 19 or 20 reaction. Carboxylic acid reacting with alcohol in acidic conditions. Fischer esterification. Esterification, right? Create the ester here. So that's gonna protect the carboxyl group like that. Cool. What is gonna be so now we see that this carboxylic acid group is now protected with this ester right there. Right? And this ester will not react with DCC. The reason why we use a benzylic alcohol is because this is a benzylic ether, you could say, that can be brought back to the carboxylic acid using H2PDC. Because that's going to cleave that bond right there, giving back the carboxylic acid and toluene, you could say as a side product. And this is one of the chapter reactions. I forgot what chapter it was. when you have a benzylic ether, and you could reduce that benzylic ether with H2PDC. It's probably chapter 22, yeah, 22. The benzene substitution chapter. That's why we use this specific benzylic alcohol to create that ester where it is a benzylic ether as well. So we can deprotect it later with H2PDC. Okay. So let me separate these protecting use and deprotecting use segments.
I think you called it like something cleavage. I forgot what.
Something cleavage? As benzylic ether cleavage.
Yes.
Ether cleavage. Benzylic ether cleavage. Yeah. Now, to bring it together, right? If we want to get to the specific alanine valine only, let's say that we are in one class, one test tube, and we just have alanine in this class. Or test tube. Okay. And if we could use, if we want to protect this amino group, we could use two kind of reagents, right? CBZ or BOT. Let's use CBZ. That's gonna protect the amino end, like that. So now this is what we have in the flask now. Right, we don't have this anymore because we converted all of this into this using CBZ, which protects the amino end. Now, if we have another test tube or another flask, and we have valine, yeah, we could protect the carboxyl end, the carboxylic acid end, using only one reagent, that benzylic alcohol with acid. Right. Which creates this ester and benzylic ether. Now we have this in the flask only. Right. Now you notice how this amino acid only has a carboxyl end, whereas this amino acid only has an amino end. That's perfect because now we can combine them, merge them together, without worrying about this amino acid or that carboxylic acid, which would lead us to this desired dipeptide sequence right there.
And then we just add H2PDC because it could clean both.
Right. H2PDC at the end, right? At the end.
Actually, just a question about that. Since you have you always talk about lab practicality.
Yeah.
Would they more often use CBZ than BOC because you can just H2PDC both the carboxy and the amino end?
Right.
Okay.
That's more green chemistry.
Yeah.
You get to save steps, save your agents, and it's also catalysts. Yeah. That's right.
Okay.
So now let's say that we get a bigger flask or like the same task, and we pour whatever is in here, in there, to here. Right. And that is going to have this CBZ and H group of H, this H2N, R group, this group right here. And we see that this is the carboxyl end, this is the amino end. We put DCC in it, and we know that DCC combines a carboxylic acid and amine together to make the amide. So let's do that, CBZ and H. Which creates this amide here, where this is the peptide bond. Okay. And now, since I use CBZ and that benzylic ether, to get to this desired product here, we gotta deprotect the CBZ and benzylic ether using H2 PDC, which gives us our desired amino acid without any mixture of products. Right? Yeah.
right next to me.
Yeah.
Like right across.
Yeah, we can also do that with VCT, but VCT would be more difficult. But because each would make a lot.
And then it gets admin degradation. Yeah. Six. And then designer.
He texted you because I don't. No. Was that because that's it?
Yeah, that's it.
Now it's a. Now it's something. Now I feel like it's almost solidified.
Is admin degradation?
I just
It's like a shortcut.
no. I think there's like a specific thing that Carahot likes to do. I don't know what it is.
Just no, general quick question. Could you do admin degradation at some point?
Like, yeah, I could do it after this this thing.
But like with the Carahot and Zurarana part, will we ever see the nitrogen peptide like coordinated?
Nitrogen peptide coordinated. Like this right here.
Yeah.
No, we won't step coordinated.
Never.
We can if we put like super strong acid, but it's not likely because when we coordinate this,
Uh-huh.
it's gonna become unstable.
Okay.
Right, with the positive charge, and it's already stable because it can do resonance.
Oh,
Or,
okay.
you know, right.
So
So
you think
usually this amide here, this peptide, is neutral.
we don't consider it when drawing like the cationic or the anionic or the Zurarana form?
Yeah, we don't consider that amide peptide bond.
Yeah.
Right. Yeah. Oh, right. Hey, if you have two carboxylic acids, one at the carboxylic, one at the side chain.
That's a good thing because I don't want to be saying different. I don't want to be
I'm trying to think of what way we could do that.
We should follow him because he was posting with the
Yeah.
and he was like nervous.
Yeah.
How are they gonna keep track? How are they gonna keep track?
Like if you
Or just like as long as
you can put that there might be any because like selectively
Well,
that,
but
but I don't know that.
I'm glad that
Yeah, but that's been like that. But I which is like use CBZ to protect
I might
obviously,
go.
I don't know what CBZ is like more like the carboxyl.
Yeah.
Have like but I don't think that was yeah.
I'm not feeling this class. I did not think anyway, yeah.
Is that my water bottle, please? Thank you.
Like,
Brian,
gave us some.
can we also use CFA for one of the deep reduction groups?
that amino acid.
Yeah.
Oh, yeah, tomato quiz.
I
I should
also
do
need
it
to
too.
memorize them for this one or two. I haven't really come with like a positive, negative.
Oh, is that another?
I mean, I wrote it down. Yeah.
Maria? Oh, I'm just basing this off of the Farhad's notes. And then I would just focus on that because Farhad like based everything on his notes and practice out. Yeah, but if your brain does that,
Yeah,
and then it could also do that as well. Yeah.
I used to too when we were doing like one.
Yeah.
No, basic too.
Oh, wait, TFA, right? TFA could be this right here. This could be TFA.
Oh, that's CFA. Oh, try, yeah,
Yeah,
trifluoro.
trifluoro.
And then, do you know what Mach is?
For Mock,
Yeah.
he didn't go over it,
Okay.
so I wouldn't worry about that.
Alright.
Yeah.
Okay, no, you definitely further than that. Look at the grade. He's like kind of right there. I know, but like, I like that. Oh my. I do think it's
I was right. Methodically check the path to sulfur and finding something on the system.
Nice everything on my test.
I don't get my big council.
Of course.
Any kind of tickets.
Test beef. Who knows? Alanine. Yes, I got it. Which one do you think it was? Yeah, it was.
Yeah, because it's well, I mean, okay, now we know what this one is.
I literally just picked that
What
one.
did you do? Give your ticket.
No,
Give your ticket. But they take it.
I did.
Okay, but you,
No, physical. You don't need a physical ticket though, right?
you need to show them your QR.
Yeah, it's in my mail. No, look at me. I have like I answered one yesterday and I was like, okay.
Yeah,
So I don't know if you noticed it. Actually, we haven't been home. But like the easel,
Yeah.
the whiteboard, I took them out of the room and I put them. But I started redrawing them, you know, answers. Yeah. I always think cysteine is serine because it has the S, but it's just sulfur. It gets me in out. Which one? Oh no. Wait, but what does that have to do with you?
Because we're spending more time with him, we might see her more often before she leaves.
Oh, I see. Cysteine. I think so. What is that? Like a basic charge. I have it written on here somewhere, or not on the test, but on the game. I have like 3 in these. I think 3 in these. Fuck.
That's like the ideal.
Yes.
Yeah.
Yeah, I haven't had some in 8 years. I had like 800 milligrams over the past week.
Oh my god.
What is it like? Okay, that's good. Okay, that's good. At least you're not taking rock.
Engine degradation.
No, it's not. It's actually insane.
260 actually.
Rockstar's 240?
Yeah.
Yeah.
I think Celsius is
Oh
like
my
200.
god.
It's actually really
Yeah.
good.
I get it.
Red Bulls. I thought Red Bulls are way more. They're like 80.
Yeah, Red Bull's that much.
I don't like that.
Okay, that's valid. It's so like the whole advertisement. They're supposed to like make you fly. We don't.
Red Bull doesn't give you legs.
Somebody sued for that, so they took it off of their commercials.
Bruh.
They had to put a disclaimer saying it's well, no, because they knew it's obviously fake, but they saw an opportunity because they didn't put a disclaimer on the commercials before.
Oh yeah. You don't have a car here?
My stats are horrible. Actually, maybe we'll start with 3-letter codes
Alright.
and the single letter codes.
Oh no, that's valid. Yeah. Yeah.
How much is it?
Oh my god.
I was thinking like physics is final things and have a paper. I'm doing some of them. So like I'm gonna be studying for bio like right after on Monday.
Yeah, but it's like
No, I'm not like sure.
you're like
Yeah. I'm not stressed about it. It's just I know I have to feel something with so.
Oh, that pisses me.
Oh, the thing is like like the roll time.
Oh my god. Okay.
Yeah.
Okay, ship defender.
Make sure to add it in your wallet soon because the QR code changes. You can't screenshot the ticket. You can't screenshot the ticket. You need a.
Go back. Like the first one, I go back and ever use one.
Imagine and never, you know, this.
Or on the yeah.
I know you're in my lab section. Do you remember to sign on the green sheet?
Okay.
No, I did not.
I didn't either. I feel so bad because like
People were telling me about it.
like I got it from Noah, and like Noah's like you 11 people are going to get like deduction, and I feel bad because he's been nice to us the entire like quarter. Yeah,
11 people are gonna get deducted?
you know what I mean? Yeah, I actually like him. It's just that no, it's because like we forgot to sign out of our green sheet like in the very last. Like we had our lockers. Yeah, he's nice. I like him.
Wait,
Like
he's
we
giving you a
had
deduction?
or yeah, because had our lockers checked, but we forgot to sign out, and 11 people, including us, forgot to like sign that sheet, even though we got it checked. I mean, it's because the one of the like the aides from the other rooms was like, "Oh, you're good." So I thought, "Oh, I'm good. I don't need to sign it."
Also, I didn't see any paper going on.
Yeah, me neither. Yeah, they didn't pass it around to me either, so I forgot about it. Yeah, it's fine. Whatever.
11 points.
Dude, hey, I'd rather take that and be done with the open series than just like bitch and whine about it and then like I'll still be on it. Yeah.
Yeah, it can't be.
I think Noah could reset it. He reset it.
No.
Okay. So we're gonna end the session with two things. Admin degradation for you and sugar closing for her. Right. So okay. So admin degradation. This is one type of reaction, like one type of reaction that can determine the primary structure of proteins, right? And there are many strategies to do that. Admin degradation is one. The other one is gonna be like carboxypeptidase. The other one is gonna be endopeptidase. But admin degradation is going to be specifically for the N terminal peptides. Okay. So if we have this peptide here with, let's say, yep, here, and plus R1 and H, R2 and H, R3 R4, and this is the carboxyl. Okay. So this is a peptide with 4 amino acids joined together, where this is amino acid 1 with its R1, amino acid 2 with its R2, amino acid 3 with its R3, amino acid 4 with its R4. And all of these bonds in blue that I'm highlighting here are the
Peptide bonds.
Peptide bonds, that's right. AKA the A-bite linkages, right? Because that's the bond that binds or links the two amino acids together. Right. this end right here, the one on the left side with the nitrogen, that's what we call the N-terminal side. We call it the terminal because it's at the end of the peptide, right? But the one on the right with the carbon here, the carboxyl end, is the C-terminal side. Okay. And if we want to determine the amino acids that make the primary structure of an amino acid, we could cut up the peptide one amino acid at a time, right? Like we could cut these peptide bonds one at a time. If we cut the amino acid at the N-terminal side first, this is Edman degradation, right? Edman degradation cuts one amino acid at a time at the N-terminal side. Right. So the reagent for that would be okay. The mechanism is going to be weird, but I'm going to show you guys the product first before the mechanism. Okay. Yeah. So when you see this reagent here, MC, 1 and 2 nitrogen, which is double 1 and 2 sulfur carbon, which is double 1 and 2 sulfur, NCS, then this is a key indicator for Edman degradation, right? Which is going to mean that we're gonna cut the peptide bond of the first amino acid at the N-terminal. And that's gonna give us this resulting peptide here. Where our new peptide is 1 amino acid short. We cut the first amino acid at the N-terminal end, so our new peptide is now 3 amino acids long, with the R2, R3, and R4, right? But the R1 right here is going to be on a side product, which is a very weird cyclic structure, right? So it's going to look like this. Right here. All Edman degradation will have this side product. Where everything here is going to be the same, or like the structure, but the R1 here is the R1 of the first amino acid at the N-terminal, right? And then from here, this is how we know what the first amino acid is at the N-terminal side of the amino acid, right? Once we know the R1, we know what amino acid it is, and then we do that again and again and again. And so we go through all the amino acids, primary sequence amino acids, right? But that's gonna be very time consuming. It's gonna like, if it's a very long primary sequence, then you have to do it a lot of times. So you can go do this reaction again, which if these were the peptide bonds, peptide bond here, peptide bond here, you would then cut that peptide bond at the N-terminal side, and that R2 would be the R2 of the next one, and then you could read that, so you could determine what the second amino acid is, right? And you do that one at a time at the N-terminal side. There is another reaction that does it at the C-terminal side, right? Cut the bond at the C-terminal side, which is a different reaction. Do you guys think Farhad is gonna go over the mechanism of this? I don't think the mechanism is gonna go over this. Yeah.
Like
His slides it did go over. It kind of does, yeah.
Like he's never asked us to go out mechanism. He's going to ask us to do mechanism.
Yeah.
Last lecture, I'm gonna ask you to do part of the mechanism.
Part of the mechanism?
We need fucking butter.
Part of
Yeah. Right.
Apparently there was a shortcut where you just having the video touch them and
Make an
then
original example.
charge go to the CN.
CN. Yeah, I see. That's shortcut. Yeah,
Yeah.
yeah. But I highly doubt that this mechanism will show up on the other test. Yeah. If it does, if the mechanism found to show up, it's probably gonna be more through the lower, like previous material.
Oh, okay.
Like the carboxylic acid, like transesterification,
Oh, okay,
crystallization, hydrolysis, all those mechanisms. Right.
Oh my god, he did that?
Okay.
You were there. You were in person. Wait, what did he do?
End of the reaction, the session with the closing the sugar rate.
Okay. Oh yeah.
I was looking forward. Oh, one of those keyboards. She's my lab partner. Yeah.
Oh yeah, and he
What
said
did he do to you?
they refused to give.
They stood their ground. Yeah. They were like, yeah, they just sat there.
They said no, and he said I
you
can find a
want to
way.
take a picture? Oh shoot! Sorry. Does anyone have a picture or?
Yeah.
Oh yeah, that's the video here. I'll post it soon.
Oh yeah, but Brian, recently apparently there were some girls that were talking really loud over him during lecture, and he gave them warnings like 5 times, and so he was like, "That's it. Can you give me your ID and your IDs?" And they were like, "No." And then yeah,
wait, Fairhat said that?
yeah, like
Like student ID or government ID?
Like student
Student
ID.
ID. Like so,
Like
like
they could identify them and
Yeah, like once early
like,
part and later.
you know.
Oh wait, during the test or
No,
no, it was
this
during the lecture.
during lecture class? They were talking so loud, and then Fairhat asked for the ID.
Apparently, and then they were like, "No."
No, they were like no.
Yeah, so obviously that's like during the whole lecture. Imagine how bad it was.
Oh my god.
So once it was out, like
Oh.
they ran out, you know.
Dang, what the heck?
Yeah. Yeah, what did your lab partner say then? If it was
She was just saying that like, oh yeah, it was the last 10 minutes of class, so we just like walked out, you know.
He's gonna make the final tough. Oh, I know. Okay, let me see her problem.
But she was saying that like some of the girls were like really scared that he would go through all like I don't know 300 students in the Oasis and like I pick them out and recognize them, but he's not gonna do that, you know. Exactly, you know, like his slides are very
oh, that's what I'm saying. Or something like that. 'Cause, look, even if they weren't being out loud, like they're still no, I would say they're still not
Yeah,
different
accidentally
than
like covers
go.
parts
You
of
know
his.
what I mean? He gave them like 5 warnings.
Like it's like here covers some words accidentally, and he like accidentally like right click and says like
Yeah,
group inspect.
he gave them like 5 different
the actual
warnings.
word.
I would have stopped at 3. that just and like from how I like heard the situation being described.
yeah.
Like if I was a professor, oh hell no.
Yeah. Okay. So let's say, oh my god. This pen.
How many cards is there? It's like
T.
it's like a fad. It's like a lipid. Yeah, polysaccharide.
Deep heart.
C3 epimer of D glucose.
Yeah.
Oh, you mean like a pearl pack from?
I feel like Farhat would name one after him if he found one.
Yeah.
Yeah.
Alpha
I would too. What?
D. Yeah.
Glucose, right?
Like Strecker, Gabriel,
Yeah.
Alpha Hardzelinsky.
Yeah.
All those names, reactions.
Yeah.
Tyson, Aldol,
Literally.
Alpha D Farhat. Parahexopyranose. Chair. Consumer.
My cousin's name is so
That's a biblical name. Filipinos. Filipinos name. So funny.
Okay. Do you guys remember the
yeah.
specific integration of D-glucose?
Yeah.
Yes. Yes. Yes.
Yeah. Everybody put them up.
Yes, everyone got pulled up at that. Something like this. Okay.
I was born doing the deep glucose sign.
So D-glucose, is it an aldose or hexose?
Aldose.
Aldose. So at the top, it should be tro, right? And is it how many carbons long is the sugar? 6 carbons long. So at the bottom it's gonna be CH2. So we would have our first two carbons, 1, 2. That means that we have 4 carbons in the middle. 1, 2, 3, 4. Right. Now, I'm just gonna draw in D-glucose here for you, which you might have to remember for the test. And to remember that, use your right hand, right?
Yeah.
Okay. And then your fingers are gonna be the direction of where the alcohol is going to. Okay, so let's try it. Let's try it together. Let's try it together. The index finger is gonna be this one. It's gonna be facing the right side. Right side. Second finger, left side. Third and fourth finger, right side. So like this. So that's how you remember deep glucose.
Woo! Trying to
Farhad asks you what you're doing. It's like, oh yeah, I'm just doing.
So on the exam, when you
Yeah,
forget what
okay.
deep glucose is, just do this on the exam. In front of them. So you know, you show them what like you know what you're doing. Do this in front of the.
Yeah. Farhad walked in.
in front of
Yeah.
the TA.
She's like, what are you doing? I'm like, I'm just doing fish.
So let's say this is C1, C2, C4, C5, C6.
What is it?
Right. Do you guys remember the definition of an epimer?
Swaps.
Where only one chiral center changes. And the one chiral center that changes is going to be at C3, which is this one right here. So this is not D-farhatose. This is D-glucose. To draw D-farhatose, we have to flip the chiral center at carbon 3. Farhatose.
Pyranos mean 5 or 6. Pyranos is 6.
1, 2, 3, 4. Carbon 3. OH. Oh, what the heck? Okay. So this is D-farhatose because we see that at carbon 3, that's the only one that changes. 1, 2, 3, 4, 5, 6. Right here. Right. Everything else stays the same. Okay. So if we want to close the ring, do you guys remember how many membered ring is a pyranose?
6.
6 membered ring. Right. 5 it would be
Pyranose.
Pyranose. Right. So the red nomenclature is the official nomenclature system. Right. But the one in blue is how I'm gonna number it when I close the ring. This cho here represents an aldehyde, which is that aldehyde right there. This carbonyl carbon is charged with positive charge, so that's my electrophile. Right, so I'm gonna number this carbon number 1, number 2, 3, 4, 5. This carbon here cannot be number 6, right? Because it has no nucleophiles that it could use, like no electrons it could use to attack that electrophile, right? So it would either have to be this hydrogen or this oxygen here, right? And because oxygen has pairs of electrons it can use to attack, it's gonna be this 6, this oxygen here. It's gonna be our 6th atom. Right. But before we close the ring, we want our numbering system to go straight down. 1, 2, 3, 4, 5, and then tilts to the right at the end. So to make it go straight down, we're gonna have to rotate these 3 groups: the alcohol, the C2OH, and the hydrogen. Right. So what direction would we have to rotate it once to make the alcohol go straight down here? Clockwise or counterclockwise? Clockwise, right here. Which forces the CH2OH to go to where the hydrogen is, which forces this H to go to where the OH is. Right. And what we're doing here is we're rotating that single bond, maintaining everything on the top stationary, the same. And when we do that, we're gonna get this rotated structure here. OH going down, 1, 2, 3, 4. Now the OH is going down, the H is now on the right side. The CH2OH is on the left side. And everything else staying the same. OH, 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 H, H, H. Right. Now, the reason why we did that is because that allows our numbering system when we close the ring to go straight down. 1, 2, 3, 4, 5, 6. Like that. Right. Now, everything on the right side is going to go down. Everything on the left side is going to go up. And the way that you can think about that is that think of this vertical line here as my arm. And I'm going to make it timber or rotate clockwise 90 degrees to the right. Right. So when I do that, like make it rotate clockwise 90 degrees, I'm going to have an OH here. Aldehyde right here. And
Hey, that's really
these four carbons are there, where this is carbon 1, 2, 3, 4, 5, 6. Now, let's look at carbon 2 specifically. If the OH is on the right side and I rotated my arm this way, would the OH on the carbon 2 be down or up? Down, right. Because if I'm rotating, if this is the OH right here, and this is my arm, and I'm rotating it this way, the OH is going to go down. Right? If you look at the hydrogen, if I rotate it this way, the hydrogen is going to go up. So everything on the right side is down, everything on the left side is up. Right. So everything down here, OH, 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 H. Everything up, H, H, H. My carbon 5, the thing that is going up is CH2OH, and I'm going to draw it out like that. Right, where this is the CH2OH. Now, I'm going to close the ring now. Having that oxygen attack that carbonyl carbon, and pop that the one into the oxygen over there. Right. But what is the geometry of this sp2 carbon? From, let's say, GenCat. Trigonoplanar, which is flat. And when this oxygen here attacks that carbon, it can attack on the top side or bottom side. Doesn't matter. Right. And if I draw this in Howard's projection, it would look like this. Right. Where this carbon here is going to be my number 1 carbon. This is 2, 3, 4, 5, 6. Where this is the new bond that was formed between them. Right. Because this oxygen here attacked that carbon, making that new bond right there. Right. And this oxygen 6 right here was attached to a hydrogen, but let's say we deprotonated it somewhere in the mechanism. Right. I'm gonna ignore 1 for now. Right. I'm gonna look at 2. 2, OH is going down. 3, OH is going down. 4, OH is going down. 5, CH2OH is going up. All the hydrogens here are gonna be implied, invisible. Right. Now, because this was an anomeric carbon, right? This is what we call the anomeric carbon. The flat sp2 carbon that leads to 2 different anomers. The OH could be on the top side or bottom side, right? But let's look at the problem here. If we want to draw the alpha anomer, do you guys remember if the OH is going to go on top or bottom? If the CH2OH is here, if we want to get the alpha anomer.
Bottom.
Down, straight. That's because we want the anomeric alcohol and this H2OH to be trans to each other to get the alpha anomer. If it was cis to each other, then that would be the beta anomer. So if the problem asks you to draw the beta diphenhydropyranose, then you would draw the anomeric alcohol on the top side, the same side as the CH2OH. Right? So that's the answer in Howard's projection, where you don't have to worry about any equatorial bonds. Every single bond is axial. Right? Now, if we were to draw it in chair conformation, you would draw this chair conformation here, where you do not have to worry about axial and equatorial bonds. Right? Where the way that I remember axial bonds is that I start at this top left corner. If I go to the next carbon, it's going to go on the opposite direction, down. It's going to alternate up, down, up, down, up, down. Up, down, up, down. If this was a carbon, that would go up, but that's an oxygen, so we don't put any bond there. But the next one will go down, like that. So those are all the axial bonds, and you don't change that. It's fixed like that. Right. So now we think about the equatorial bonds. It's going to be on the opposite direction as axial bonds. Right. So if we look at this carbon here, the axial bond is going up. That means the equatorial bond will have to go down. But the direction matters here because it would be parallel to the second bond they don't touch. So what I mean by that is that if you look at this curve right here, ignore this first bond that is attached to, and look at the second bonds. These bonds right here. Equatorial bond is going to be parallel to this bond and that bond like that, right? Which is parallel. And it's going down like that as well. Right. So since it's a Fairhouse class and not Leavens class, I don't think he'll make you draw these pair conformers. So I'm just going to give you guys the equatorial bonds. But for Leavens, I don't know if you guys had her for Wednesday night, but she like made you draw these out specifically, and she like worried about the equatorial bonds a lot, like the angle of them. Right. So now let's go back to the groups where let's say this is atom 1, 2, 3, 4, 5, 6. If atom 1 alcohol is going down, where would that alcohol be at? Axial or equatorial? Axial. That's right. I could draw hydrogen here. How about carbon 2? Where would the alcohol be? Axial or equatorial? Equatorial, because alcohol at carbon 2 is going down. If we look at the char conformer, we have to check which one is going down, axial or equatorial. Axial is going up, equatorial is going down. So we have to draw the alcohol equatorial, right? So in Howard's projection, every single bond is axial. But when we convert it to char conformation, it could be equatorial, but the direction has to stay the same, right? The direction is the most important thing. If this is down, it has to stay down. This is down, it also has to stay down. But it's no longer axial, it's equatorial on a char conformer. How about carbon 3? What would alcohol be at carbon 3? Axial. Carbon 4?
Equatorial.
Equatorial. Carbon 5? Equatorial, but it's not alcohol, it's a CH2OH. Yes. So this is the answer in chair conformer. Yeah. Yeah, on the far is. Can we take a quick picture real quick? Yes. Yeah.
That will my game.
Let's go.
I'll take a picture.
Oh yeah, yeah, thank you.
Yeah, yeah.
Can I get them in the picture too?
Yeah. Let's include them too.
Yeah.
Let's draw D-glucose. D-glucose.
Okay, a couple D-glucose guys.
Oh yeah, let's do D-glucoses. Yes, let's do it. Let's do it.
Okay.
Okay. I was just wondering if you guys we're gonna do it now, so I didn't do it. I was like, I know. I was like, oh shoot, is anyone gonna do it? Yeah. Okay. That's good. Yeah. I get this. It's D-glucose. Yeah, it's D-glucose. Yeah.
Thank you so much.
Yeah, no worries. Good luck on the final. Yeah.
Driving up all the way up here.
Yeah, no worries. Yeah, that's fine.
Good luck on your finals too.
Yeah, thank you. 9 finals next week.
No.
Yeah.
Oh my goodness. So, yeah.
Most of them are S, right? For
Have a good dinner.
Thank you. S, yeah.
it's
O, R, right.
but like it's attached to like
We're gonna see, like,
CH2S,
slightly-
but I don't understand why the higher priority is.
Right, because it's a CH2, right? But if you convert to the C of the carboxylic acid, it's still a C. So now which was it attached to? The cysteine is attached to S. The carboxylic acid is attached to oxygen. What has a higher sulfur or oxygen? What has a higher atomic number? Sulfur. So that's why the sulfur, the one in the side chain, has a higher number than the carboxylic acid.
Nitrogen has the highest.
Yeah, nitrogen is still the highest one. Right. But the carboxylic acid is no longer number 2. It's now the side chain of the cysteine, the one with the sulfur. Yeah.
Was this recording like from the moment I put it like the thing in? Or?
Oh yeah, it was recording. I finally put it. Yeah.
You put it in the beginning because like earlier I was just like on my laptop trying to figure out my photo booth.
Yeah.
And my photo booth was supposed to selfie something.
Yeah. Okay. I'll cut that out. I'll cut that out. Yeah. Can you send it to me through my email?
Yeah.
Yeah. Thank you. I'll cut it out.
Wait, is it on my laptop or?
It's on your laptop. Is this Zoom? Like, did you record it on your laptop or the cloud recording?
I think it's on Zoom, so like I'll take my laptop. So I can also tell you this one.
Okay. Yeah.
It's like that one also. Did that one save the recording to my laptop? Or I'm good.
Oh yeah. The mic. The mic.
Oh, it's a mic.
It's a microphone. It's a microphone. Yeah.
Never mind. I don't think
Yeah,
I
yeah.
cut it then. I think it's good.
Oh yeah. This didn't record your screen. It didn't record your screen. Yeah. No worries. Yeah.